Okay, hello all you crazy people out there. My name is Michael, I like wizards and dragons and making games, and welcome back to 3D Games in GameMaker. Today we are not going to be working on 3D collision code itself, but instead we are going to be working on some of the foundational building blocks that will allow us to work on 3D collision code in the future. This is what the little demo project that I'll be using right now looks like. It is just a 3D grid in a 3D world, and we can rotate the camera around the center point and zoom in and out and all that good stuff. I'm not going to be very concerned with that right now. Today, if I can zoom in on the resource tree a little bit, I'm going to set up a few scripts. The first thing that I'm going to do is write myself a little vector library. I am going to call this... I'm just going to prefix everything with COL_, at least all of the scripts. I'm going to write myself a little vector math library. If you already have such a thing, with all of the functions that it will be helpful to have in a vector library, you can use that instead. But for now, let me just run through this real quick. I am going to create myself a struct. We will be using GameMaker Studio 2.3 for this, by the way. I'm going to assume that everybody's okay with that at this point. 2.3 has been out for like 9 months now and over a year in beta, so I'm pretty sure everybody should be on board with it by now. Function vector3. This is going to be a constructor. It will take 3 arguments, x, y, z. The parameters self.x can get assigned to x, self.y can get assigned to y, self.z can get assigned to z. That is simple enough itself, but there are a bunch of math functions / methods that we need to add. Once again, I will reiterate from episode 0 of this series that I will not be writing 100% optimal code in this 3D collision series. Instead, I will be erring on the side of readability wherever and whenever I can, and that does mean using things like structs and some more object-oriented programming rather than arrays and some more imperative programming, which you may find to be slightly more performant. So let's start with the basics. Let's start with just arithmetic. I will be creating some methods add. We will also have, and I guess I'll just start with this one. Add is going to take an input, and it is going to add it to the current vector3. So it will return a new vector3 with the components being self.x plus val.x, self.y plus val.y, self.z plus val.z. Okay, each one of these functions is going to not change the state of the vector3 itself, but it is instead going to return a new value. Some of those new values may be vectors themselves. Some of them may be scalar values, single numbers. There's going to be sub for subtraction, there's going to be mul for multiplication, and there's going to be div for division. And let me just go through here and update each of the operands that we will be using.
Hey.
So use the minus sign for subtraction, use the multiplication sign, the asterisk for multiplication, and using the slash for division. Okay? That is the basic arithmetic. So, in addition to just taking other vector3s as parameters to these arithmetic functions, you can also, the rules of vector math do allow you to take scalar products and return the result component-wise. And for example, if you were to multiply a vector3 by a scalar, each of the components of the vector3 would be multiplied by the same scalar. I am going to include support for this when it comes to multiplication and division. I am not going to include support for it when it comes to addition and subtraction, because I don't think it's really going to be necessary. So if is real, I guess you could say is numeric. Is numeric is a function, right? Is numeric is also a function. If the parameter that you pass the multiplication function happens to be a scalar value, we will instead return, and I can't believe I forgot the actual return statement itself in these lines. Who was watching me and screaming at your monitors, waiting for me to notice that? We will return a new vector3, and that will be self.x times val, self.y times val, self.z times val, and we can do something very similar for division. And that is going to be, instead of the multiplication asterisk, the division /. Alright, addition, subtraction, multiplication, and division. Those are the 4 basic arithmetic operations. The next vector method which we will be implementing will be static magnitude, and this is a method which will return the magnitude, basically the 3D direction of the vector. That needs to be an equals function. The calculation is basically the Pythagorean theorem in 3 dimensions, but GameMaker actually has a built-in function to do this, so we don't really have to do the actual math. We could just say return point distance 3D, and the x1, y1, z1 can be the world origin, so 0, 0, 0, and x2, y2, z2 can be the components of our vector, so self.x, self.y, self.z. I am going to be using, by the way, for my code naming convention, I am going to be using Pascal case for at least for all of these struct classes. Pascal case is the naming convention where there are no underscores, unlike you often see in GameMaker, and the first letter of every word is capitalized. So magnitude starts with a capital M, and vector 3 starts with a capital V, and that sort of thing. You don't have to do this, but as long as you have a code naming convention which is consistent with itself and that you yourself can read, that is the most important part. I just figured I should draw special attention to that. Another function. And also, all of these methods are going to be static. Static methods, I made a video on those some time ago. It won't really affect the performance of the game, but it does affect how GameMaker internally stores them in memory, and it can slightly reduce the overall memory footprint of each of these vectors 3s, which can be a desirable effect. So all of these methods are going to be static. Anyway, similar to the magnitude method, there is going to be a distance2 function. And the distance2 function is going to be much like the magnitude function, except it's going to, instead of just returning the length of the vector, it's going to return the distance between two vectors. So this is also going to take a parameter, which is going to be another vector 3. And we can say return point distance 3D. And instead of starting at the world origin, we will start at the other at the position of the other vector 3, and we will be looking at a destination of ourselves, self.x, y, and z. Okay, that'll come in useful once in a while. The dot product, another extremely common function to have in a vector library. The dot product is something that we will be making extensive use of over the course of the series. The calculation for the dot product, in case you're curious, is something like val.x times self.x plus val.y times self.y plus val.z times self.z, and that's actually a calculation that I can just write out from memory, unlike some of the other ones. But GameMaker does have a built-in dot product 3D function, and this will actually perform slightly better than doing the math ourselves, because this is a function that's built into GameMaker, and it will perform better than just regular GML. This also takes 6 arguments, much like the point distance 3D function does, which are going to be basically the components of 2 3D vectors. So we can say the dot product of self.x, self.y, self.z, and val.x, val.y, and val.z. In addition to the dot product, we are also going to be using the cross product. The cross product is something I have not really talked about on video before, and it has a calculation which is somewhat more ugly than the dot product. It also is going to take another vector 3 as a parameter. GameMaker doesn't have a built-in cross product function, does it? It does not. Alright, that means I'm going to have to write it out myself. If you want to just copy and paste this code, I will not be offended. This calculation is actually going to be rather ugly. What the cross product does in a nutshell is, instead of comparing 2 vectors the way that the dot product does, is it will take 2 3D vectors and return a third vector which is at a right angle to both of them. This is rather useful for things like generating surface normals for triangles, or triangle-triangle collisions, as we're going to see later on. Let me see. And if I can type this out on the first try correctly, I will be slightly surprised. A new vector 3. Okay, did I get that right on the first try? Self.y times val.z minus val.y times self.z. you can sort of imagine these components crossing over each other. Self.v times self.z times val.x minus val.z. That should be a times self.x. I did not get this right on the first try. And thirdly, self.x times val.y minus val.x times self.y. Okay, that looks like the cross product. Again, if you want to copy and paste that calculation instead of trying to spell it out on your own, I will not be upset at you. All right. The last two that I want to implement for vectors are going to be slightly easier. One is going to be equals. This is just going to be a little helper method. You cannot use the equals equals operator to compare to two vector 3s or any other two structs in GameMaker, because that will just compare the references to each struct, and that will not compare the actual components of the struct. So if you want to compare the actual components of a struct and see if one is equal to another, we will need to implement this ourselves. Return, and this is going to be a Boolean expression. Self.x is going to be equal val.x. So we're going to be comparing the two x's. And self.y equals val.y. And self.z equals val.z. Alright, that's going to compare the x, y, z, return true if all three of them are equal to each other. And lastly, the last method that I want to do, at least for now when it comes to vectors, is going to be static normalize. And that's going to be a function that is not going to take a parameter. Instead, this is going to return a vector which has the same direction, the same overall bearing as the current vector 3, but it's going to have a unit length of 1. And we can do that by saying var magnitude is going to equal self.magnitude, and we can return a new vector 3, which has the same components as we do, just divided by magnitude. So self.x divided by mag, self.y, same thing, self.z divided by the magnitude. This will produce a bunch of not numbers if you have a vector which is exactly 0, since in that case all of the components will be 0, and then the magnitude will be 0, and 0 divided by 0 is not a number. Nan, and you will have a vector 3 that's composed of a bunch of nans. If you want, you can check if mag equals 0, return undefined or something, but you don't have to. None of the code that I'm writing should run the risk of doing that, I don't think. Unless you pass in like a bad surface normal or something like that, but nevertheless, we'll be starting with this. So this is all I want for vectors right now. If I run the game, nothing's going to happen. You could set up unit tests for all of these if you want, but I do not have the patience to set up a bunch of unit tests right now. I have my notes for what to write on the other screen over here, so I'm just going to hope it's correct. Let me commit this change as added a little vector library. Okay, so that's one part of what I want to do today. Another part of what I want to do today is going to be defining some basic shapes. Let me create another script. Let's call this call_shapes. We're going to be starting with, rather than 3D objects that you load from a 3D object file like an OBJ or a Collada or something like that, we are going to be starting with some primitive shapes. And those primitive shapes are going to be spheres, axis line bounding boxes, which are basically rectangles which cannot be rotated, rectangular prisms which cannot be rotated, cubes and that sort of thing. Planes. So planes are a 2D sheet which extend off into infinity, and individual zero-dimensional points in space.
Hey.
And first we're going to be starting off with some simple collision checks with those basic shapes. 1, because the math is easier, and 2, because they are much faster to calculate than things like a mesh of triangles. And we're also going to be doing ray casts and line casts into those shapes so that you can see if, for example, a bullet that you shoot out of a gun in a first-person shooter, if something traveling in a line would intersect one of these shapes in 3D space. So first, let's see, I am simply going to define the shapes, so I'm going to create a bunch of other structs, function, and I'm going to call these things like call point, short for collision. I'm just going to probably prefix most of the classes except for the vector3 class in this little project with COL for collision. There's also going to be the sphere, As I said, the axis-aligned bounding box, which I'm going to just abbreviate as AB, because there's no way I'm spelling that out every time, and plane is going to be the fourth one. Next, and I can add a little, like, comment at the top, calling those some basic shapes. Next, I'm also going to define classes for lines, 2 different kinds of lines. So those can be call ray and call line. Unlike the lines that you may have learned about in geometry class in like 6th grade or whatever, we're actually going to be looking at line segments. Lines are, at least the way that I learned about them in geometry, they extend to infinity in both directions, whereas a line segment has a defined start and an end point, which is what we're going to be doing. Next, let's actually write a little definition for each of these shapes. So a point is simply going to be defined by a single vector 3, which is going to be its vector 3's point in space. So I'm going to give that a single parameter, which is position. And in the top of the constructor, we can save that to a instance variable, to an instance variable. Spheres are basically big points. Spheres are basically points with a radius. So we still have our origin point in space. And we are also going to take a radius. I hope you all don't mind my joke that spheres are basically big points, because I'm probably going to be making it at least a couple other times in the series. Moving on, axis-aligned bounding boxes. There are 2 ways that you may want to define a rectangular prism in 3D space, a cube or something similar. You may want to start with a minimum and a maximum point, so basically an x1, y1, z1, and an x2, y2, z2. I'll have a little diagram on the right half of the screen so that you can see what I mean. Or you can also define an axis-aligned bounding box as having a center point, a central position, and essentially a width, height, and depth, or as I'm going to define it here, a half width, height, and depth. So we can give this constructor a position, and which is going to be a vector 3, and also I'll call it half sides. No, I'll call it half, I forget what game physics cookbook called it. I think it was half extents. All right, and self.position is going to be position, and self.half extent, plural, is going to be half extents. Planes are a little bit different. Planes are not something you might think of when you think of a shape. Planes are an infinite 2D sheet, and they're defined by a surface normal, so a direction that they're pointing, and a distance from the world origin. It doesn't really make sense to give a plane a 3D point in space as its origin or anything, but you can define its closest point to the world origin and how far away that is, which is what we'll be doing right now. So first, normal is going to be a parameter, and the distance from the world origin. And self.normal and self.distance are going to be its 2 parameters. Next, the lines, the line types. Rays are defined by an origin in space and a direction that they're traveling in, basically normal. We can assign those two values as parameters to the ray, which are going to be, I'll call them origin and direction. And line segments are defined by a start and an end point. I would love to call the 2 parameters start and end, but end happens to be a reserved word by GameMaker, so we can't use it as a variable name, so I'm just going to call it start and finish. Like that. Just in case you want to remember which types each of these parameters are, we can leave a little comment saying what type each of these parameters are. Like this. Most of them are going to be vector 3s. The only one that's not, as for the basic shapes go, is going to be the plane's distance from the origin. This is going to be a vec3, as will this, and the ray and the line. Okay. Later on, I will most likely be adding other shapes, such as capsules and oblique bounding boxes, so that you can have... do I really want to call it this for the rest of the series? So that you can have an ab that's rotated in space. You're welcome for the mental imagery. As well as naturally triangular meshes, so that you can actually load a model in for collision purposes. Next, I am going to commit this change. Let me just say I define some basic shapes. Next, I am not going to implement any collision detection right now, but I will implement some setup, which is going to be the structure of how we're going to implement them later. So each of these 4 basic shapes, points, spheres, abs, and planes, are going to be able to collide with each of the other 4 basic shapes, as well as rays and lines for ray casts and line casts. So I can say in call point, static check point is going to equal function. And this is going to be filled in later. We can also say check sphere. It's going to be a function which takes a sphere as a parameter. Check ab is a function which is going to take an ab as a parameter, and check plane is a function which is going to take a plane as a parameter. And for the different line types, we can say check ray and check line. Like this. Okay? And this is going to be copied and pasted into each one of these other basic shapes, into the sphere, into the ab, and into the plane. Rays and lines will not be will not be checking anything, at least from their perspective. You can do math to see if 2 rays or 2 line segments intersect in 3D space, but for the purposes of 3D collisions for a video game, we will not be adding rays and lines to any sort of collision world later on when I get down to organizing these things into a hierarchy. So we will not be having rays and lines check for collision against each other. Maybe as a bonus episode later on we can do that or something, but it's not important right now. Alright, this wasn't actually all that much work. It was mostly just a bunch of copying and pasting, but I'm going to make a commit that says leaves space for collision checking functions. Okay. How long have I been recording for? Alright, not that long. So to give these videos a little sense of progress, I'm going to draw myself on paper a little chart, a little matrix, not in the mathematical sense, but I'm going to draw myself a little chart, which is going to have all of these basic shapes on them, as well as some other things, and over the course of the series, I will be checking off each of those little boxes as we make progress, as we implement each one of these collision shapes, as we implement each one of these collision checks. And as the series goes on, we will fill in all of the basic shapes. We will fill in triangles and the basic shapes and triangles in themselves, and the different ray casts and line casts and that sort of thing. And hopefully it should be at least a little bit motivating to look at. You can draw one yourself if you want, and it should give us a little sense of progress as we fill things in. Now, you may observe that a couple of these collision check functions, methods, are a little bit redundant, and that we have defined the same thing in a couple places. And in fact, we can actually, right off the bat, without actually doing anything else, remove just under half of these. Just under half of the amount of work that we have to do. And I won't check off the boxes on the grid now, because that's just cheating. But for example, we have a point.checkSphere in the point class, and also in the sphere class we have sphere.checkPoint. And as you can imagine, the math that will go into both of those things is going to be exactly the same. So instead of bothering to implement it twice and to have to go and edit the code in 2 places, if we want to change something, refactor, or fix an error or something, we can say in sphere.checkPoint, we can simply say point.checkSphere, and we can pass ourselves as the parameter, return that value. And now both of these functions, both of these methods basically refer to the same logic that we will be writing in the code. Likewise, down here in ab.checkPoint, we can simply turn around and say return point.checkAb. Please don't leave any comments about that. In ab.checkSphere, sphere.checkAb, ab, passing ourselves in as the parameter. Planes can do the same thing. Point.check plane. Sphere dot check plane, and ab dot check plane. I'm suddenly forgetting to actually write in the return statements themselves for some reason. Don't ask me why. I'm not usually one to forget those things. And this has right off the bat cut down on the amount of functions that we have to implement by a decent amount. I want to say that's about a third. There are 1, 2, 3, 4, 5, 6 times 4. There are 24 collision functions, which I've written a little definition for. And right off the bat, we have filled in 6 of them. So that's going to be a quarter of them have been filled in. Cut down from 24 to 18. Hooray. Okay, that can be a commit as well. Would that be added some redundant functions or remove some redundant functions? Let's go with remove. That sounds better. All right, the last thing I want to do is write a couple different helper functions and methods. One of them is, for example, in case you do want to define an axis-aligned bounding box by a minimum point and a maximum point, let me go and create myself a new script. And I'm going to call that helper functions. And we can define ourselves a function which says I'm going to call it new collision axis aligned bounding box from minimum and maximum. And this is going to take 2 parameters. One is going to be point min. Again, I would love to just call it min and max, but those are functions. Those are built into GameMaker as functions, and I do not believe I am able to use those as variable names. Point max. This is not a constructor because we do want it to actually construct a regular axis aligned bounding box and return it instead of being the constructor itself. But we can calculate what should go into those. So the center point would be basically the average between the minimum and maximum points. So we can say var center position is going to be, and you can do the math yourself. You can say new vector 3 with point min.x plus point max dot x, what am I even doing, divided by 2 and all that. You need parentheses in there somewhere. Or we can make use of some of the actual vector functions that we wrote, some of the vector methods. So we can say center position is going to equal point min.add point, where are my fingers on the keyboard, max. And this is going to return a new vector 3, and from there we can say a div and by 2, so we can take the average. And this is going to be a much more elegant way of adding the x components of those 2 points together and taking the average, adding the y components of those vectors together, taking the average. It's a nice little abstraction layer, makes the code a little bit more readable. If GameMaker gave us operator overloading, it would be even nicer, but alas. And we're also going to need, in addition to the center position of the axis-aligned bounding box, ab. I said I was going to call it ab. We're going to need the half size, and that can be point max dot subtract point min. And once again, since we are going to be this is going to be like the half width, the half length, the half depth instead of the full thing, we can take the result of that and divide by 2. And then we have the 2 parameters that we can feed into the collision ab constructor. Is that it? I missed a letter somewhere. And those are the center position and the half size. Okay, so now you can define an ab in terms of both an origin, a central position, and a half size, or in terms of a minimum and maximum point. Okay, you may end up, if point max is less than point min in this function, you may end up with like negative half size, a negative half size, but that shouldn't change the math, I don't think. Okay, you know what? Just because this is going to be bothering me if I don't, but let's just add another vector function for static abs, and that's going to be the absolute value, and that is going to return the absolute value of each of our components, self.x self.y and z, so that each of these will have a positive. That needs to be a semicolon instead of a regular colon, so that same down there. So that each of the components will have a positive value. All right. So half size can be the absolute value of point.max subtracted point.min divided by 2, and we can take the absolute value. Next, it can be useful to be able to obtain the minimum and maximum point of an axis-aligned bounding box. So where are we? Where's ab? Down here, we can write some methods for that go inside the ab class, and that can be get min. It's going to be a function, and get max. It's going to be another function. And these are going to both return vector 3s. You probably see where this is going. If we have an origin point and a half extent, we can return self dot, what did I call it? Position, self dot position dot subtract self dot half extents. I am using snake case, which is all lowercase, use underscores for parameters and variables, just not for classes and methods. By the way, in the series, that is how I generally use GameMaker. Would that be confusing? Should I keep using Pascal case? I'll keep it like this for now, and if anybody doesn't like it, I can address it later. Okay. Anyway, the minimum point in the axis-aligned bounding box is going to be the central position minus the half extent, and likewise. The maximum position is going to be the same thing, but we're going to add the half extent instead. Okay. The next helper functions I'm going to add are going to be in the line class, just the length of the line segment. So static length is function, and this is not going to be an overly complicated calculation. It's just going to be the distance between the start and the end points. We've already written a method in the vector class that allows us to do that very easily indeed. And instead of having to actually calculate the distance ourselves, we can just say self.start.distance to self.finish. And that is going to return the distance between these two vectors, and that is going to be the value that we're looking for. Alright. Let me just look over this real quick, just to make sure that all the code is correct, and nothing sticks out to me as being extraordinarily wrong, because that would be embarrassing. I don't see any issues. The one that I'm especially worried about is the cross product, because this is such a long calculation, and I am not used to having to memorize this. But yz minus yz, zx minus zx, xy minus xy, I think that's correct. Alright, as I said, the components are sort of crossing over each other. Is that it? If you want to, and I don't personally find this especially useful, but in the same way that we're defining an axis-aligned bounding box from a minimum and maximum point optionally, if you want to, you can also obtain a ray from a line. Actually, I'll put this in. No, I'll leave it here. Function ray. I'll call it new call ray from points. And this can also be a start and a finish. Ordinarily, if you have a start and a finish, you would be using a line segment. But in case you wanted to turn a line segment into a ray or something like that, you can do that. The start point would just be the ray's origin, so that would just go into the ray constructor verbatim. The start position for the origin, and the direction is going to be. I'm going to call it direction is going to be the difference between the finish and the start. The finish and the start vectors. You can normalize this if you want. Sure, why not? We can have a normalized direction vector. That's fine. It doesn't really matter. And we are going to return new call ray with the start as the origin and the direction as the direction. All right, those are my helper methods. There, I believe, will be others that we will be doing. later on once I get to the other shapes, which are not points, spheres, axis line, bounding boxes, and planes, but that can wait for another day. This recording section is going on 50 minutes, and I would like to end it off. Next week, we're going to be playing with points. Next week, I'd like to also get to spheres, because spheres are, as I said, a lot like points that are just bigger, and the math tends to be rather similar, but we'll see how much time we have. I will not be making a video that's an hour long just for the sake of squeezing points and spheres into the same video. The code for this, let me commit this last change. Added some helper. The code for this will be in the video description. Look for the 0.1 release, which is going to be the boilerplate setup. Alternatively, you can look on the branch for week 1, which by the time this video goes public should be merged into the master branch. Subscribe if you want to see more. I post about 2 game dev videos a week, one of these and one Let's Make a Tower Defense game, which is in a lot of ways putting the theories in these in the tutorial videos into practice in an actual game. I also post a whole bunch of Let's Plays if that's something that you're into. Other than that, I have a Patreon, so if you want to contribute towards these videos being made, there will be links to that in all the usual places. I hope you all are looking forward to seeing more, and I will see you all later. Special thanks to Kiara Elizabeth, Connor, David Key, Edward Holt, Emily Koyo, Halo Factory, Posho, Tusk, and Zenith for supporting these videos. If you want to see your name in the credits or to hear yourself shouted out at the end, head on over to the Patreon page down in the video description to join the fun.